Let's begin with the activity, bring some of you up to date with your ears. If we have the 2x2 array of points, we get one square out of it. We're to the 3x3 array. We're able to get, how many was it? 6, because we had 4 size 1s, so to speak. One size 2x2.
So we don't have 2x4s?
And no, you don't have to display them. And one there, makes a total of 6. When you go to 4x4, how many do we get? Well, then you'd be wrong. However, it's better for me to say that facing the board than facing you, so I don't identify the person who missed that. However, I know the voice. But what are the 2 you missed is the question. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. 1x1s. 9 1x1s. Which means we have 4 2x2s and 1 3x3 as far as the dimensions of the squares. Okay, and we pick up these, and we have 4 of those. 1, 2, 3, 4. So we have 4, which are root 2 by root 2. And there's your 18. Okay, now it would be vertical. You can lean at 45 degrees. Let's say you can't lean something more or less. So if I lean about there, and if I lean to the right, I can lean to the left. And each of those, let's see, are root 5 by root 5. And there are 2 of them. So the correct answer for question 3 is, I guess, 20. So that only leaves you a few more to do. How many? 4, 5, 6, 7, 8, 9, 10, 11. And possibly come up with an equation that then you wouldn't have to count. But until you come up with the equation, you have to count. But remember, the activity is open note, open book, open friend, open whatever resource you can find. Because I think problems like this are kind of interesting. Yeah. So, let's look again at simple function. Let's say f of x equals 2x minus 1. And this one's easy to graph, because in slope y-intercept form we have a y-intercept of -1, a slope of positive 2, and we have our line. Of course, we need labels and scales, so that it is correct. So if we modify this a little bit, say g of x equals 2x minus 1 times x plus 1, oh no, let's say x minus 1. X minus 1 over x minus 1. Then g of x is very similar to f of x, and in fact is the same as f of x except for a single point. So its graph has a y-intercept of -1, a slope of positive 2, but 1, it's got a hole in it. have pretty much the same shape, except now we have a gap. This one, when we draw it, we have to somehow show that gap, which means we've got to pick up our pen if we're leaping over that. Okay. Like, what was that? Burt Reynolds movie where they're bringing the beer someplace. Smokey and the Bandit. He jumped this creek. Of course, they destroyed the car on landing, but of course they just replaced it with another car. You don't see it. I read someplace in Dukes of Hazzard, during the several years of production of Dukes of Hazzard, they used 57 different cars for the, they had their jumping cars and their crashing cars. And looked good car. Okay, one more, h of x. H of x. I'm going to do 2x minus 1 times x plus 1 divided by x minus 1. Okay. Now, in h, x minus 1 does not divide out. So here we have a missing point. What does this denominator cause at x equals 1? Besides division by 0, how does that represent on the graph? An asymptote, it's a vertical asymptote. So, in sketching its graph, at 1 has vertical asymptote. But what does it do elsewhere? Well, let's go multiply the numerator out. H of x is equal to, let's see, 2x squared plus 2 minus 1 is plus x minus 1 over x minus 1. If I divide the denominator into the numerator, and here I think I'll use long division today just because x minus 1 divided into 2x squared plus x minus 1. X goes in 2x squared 2x times. Keep your column alignment and your place value alignment. 2x times x is 2x squared. 2x times negative 1, negative 2x. Subtract. X squares go away. This becomes 3x. Bring down the next term. Excuse me. X goes to 3x 3 times. Multiply back. 3x minus 3. Subtract, give positive 2. So this thing behaves like the line 2x plus 3 with a small addition. I say small addition. That small addition, when x is close to 1, is a very large addition. But when x is very, very large, that makes the denominator very, very large, and this approaches 0. So, out in the extremes, when this approaches 0, this thing behaves like the line y equals 2x plus 3. Come back over here. 1, 2, 3. Y-intercept of 3, slope of 2. 1, 2. So, we have a what they call an oblique asymptote. I will call it a slant asymptote, but it's the same thing. And if we examine the equation a little bit, does this have any zeros? Let's see, 2x, let's just look at the numerator. 2x squared plus x minus 1, that equals 0. Does it factor? Sure, it factors. It factors as 2x minus 1 times x plus 1. Well, this says it has a 0 of the function at x equals 1/2 and at x equals -1. So at -1 and at 1/2, it has zeros. We have a vertical asymptote it cannot cross, and we have an oblique or slant asymptote that it does not cross. So how do we sketch this thing? Well, we have to include those 2 points. What's the y-intercept? The y-intercept is when x is 0. So, -1 times 1 over -1 is +1. Okay. So we have a y-intercept, 2 x-intercepts. This is an asymptotic line. This is an asymptotic line. So we draw a smooth curve. But we also have points to the right of the vertical asymptote. If I pick something just slightly greater than +1, end up way up here. So basically it comes down and has the same shape above as it does below, as it takes off like that. Sometimes it's hard to find a good vertical window to show both branches when you're doing this, if that branch is too high. Okay. So, all of these essentially have the same factor, 2x plus 1. This one, just a missing point. This one, it's a huge, not just a hop, it's an infinite jump from -infinity to the left of the vertical asymptote to +infinity to the right of the vertical asymptote. So, talk about continuity. This function is continuous. This function and this function are not continuous. Even if I take the first function and make it not the first function, I mean the second function. Time out. Leave the first function as it was. Even if I take the second function and make it piecewise defined, okay. So if I piecewise define this function, it is a line 2x minus 1 everywhere except when x is equal to 1. When x is equal to 1, so it's -1, just because. I did that just so we can see that the domain of this function is all real numbers, but it's not continuous, even though the domain is all real numbers. This domain, nothing I can do to repair that to fill in this huge gap. Because if you have a step, you can't fill that step in with a single point. So what do we need for a function to be continuous? At a point. And it's a pretty easy definition. f of x is continuous at x equal a if the limit as x approaches a from the negative side of f of x is the same as the limit as x approaches a from the positive side is equal to the function value. Those three things must be true. The limit from the left must equal the limit from the right must equal the function value. Over on our original line, wherever you are, whatever point you find yourself, the limit coming in from the left is the same as the limit coming in from the right, same as the function value. For every point on that curve. So every point on this curve, which happens to be a line, every point on this line, the function is continuous at that point. If it's continuous at every point of the curve, at every point of the domain, then we say it's a continuous curve. But if we have any discontinuities, then the curve is not continuous. This one clearly, the limit from the left as it approaches positive 1 is negative infinity. As it approaches 1 from the positive side, it's positive infinity. So it doesn't meet, wherever I had it, I wrote it down someplace. Did I erase that already? Oh no, it's over. First thing, did I erase that already? It doesn't satisfy this first part. The limit from the left is not the same as the limit from the right, so it's not continuous. But the middle one, it satisfies the first pair of conditions. As we approach 1 from the left, the value of that limit is 1. As we approach 1 from the right, the value of that limit also is 1. So it meets this portion, but it doesn't meet that portion. Because the function value at that point, I chose to be negative 1. And since negative 1 does not equal 1, it doesn't satisfy all the conditions of continuity, so this is not continuous. Okay. Now, we can have pieces which are continuous. Excuse me. Everything to the left of negative 1 can be considered as a continuous subset of the function. Everything to the right of positive 1 can be considered continuous. But if there's any point which is not continuous, even though the individual pieces may be continuous, if there's a single point or more which is not continuous, then the graph is not continuous. The function is not continuous. Same thing here. Everything to the left of negative 1 is continuous. Everything to the right, everything to the left of positive 1 is continuous. Everything to the right of positive 1 is continuous. But we have this huge discontinuity at 1. So the function as a whole is not continuous, even though piecewise it is. Okay, so there's one requirement for a continuous function, and we say f of x is continuous if f of x is continuous at all values. So if we have a gap or a jump, it's not continuous. Piecewise, let's look at the floor function, for instance. you're at floor 0 until you're suddenly at floor 1. You're at floor 1 until suddenly you're at floor 2. You're at floor 2 until suddenly you're at floor 3. And similarly, you're at basement level 1 until suddenly you're on the ground floor. And you're at basement level 2 until suddenly you're at basement level 1. So even though there are infinitely many discontinuities in this case, all the intervals, like from 0 to 1, the interval, x element of 0 to 1, open interval, that interval is continuous. Or element of 5 to 6, open interval, that's continuous. But it's not continuous at any integer. Not continuous at 2, because you come at 2 from the lower side, from the left, the limit is 1. Come at 2 from the upper side, the limit is 2. Since 1 doesn't equal 2, is not continuous. Whether this happens at a single point or infinitely many points is continuous. About the most complex function I can think of that is easy to perceive but hard to sketch. Let's simply say f of x equals x if x is rational. And it's equal to 0 if x is not rational. So, plotting 2 points. 0 is rational, so it's there. 1 is rational. Oh, I'm sorry. 0 is rational, so I don't mean, let's make it just a constant 1. So at 0 we get 1. At 1 we get 1. At 2 we get 1. At 3 we get 1. At 1/2. At 3/4. At 1/4. At 11/9/16, whatever that would be. 11/9/16. And because of the thickness of your points, it would look like you have a solid line. Because no matter what 2 rational points you give me, I can find a rational point between them. Just add them up, divide by 2, and you have a rational point between them. And you can do that infinitely many times. So no matter how close you look, no matter how small a neighborhood that you look in, there are infinitely many rational points in there. A countable infinity. Kind of went over that last time. But, having said that, between any 2 points, there are also infinitely many irrational values. And it turns out there are more irrational values than there are rational values. So if we drew open circles everywhere that's not continuous, we'd have a blur of intersecting open circles we'd have a blur of intersecting open circles up here on a solid line, apparently solid line down there. So visually it would look like we have a solid line at 1 and a solid line at 0. No matter how close you look, this would look solid, but has infinitely many holes in it, all the irrational points. No matter how close you look, this would look solid, but has infinitely many holes in it, the rational points. So, just because it has the appearance of being continuous, if it doesn't meet the definition, is not it's not continuous. So we have continuous functions. Excuse me. Now let's go back to college algebra. You guys remember college algebra? Pre-calc, algebra 2 maybe. And one of the things we dealt with in college algebra were polynomials. And that nice thing about polynomials is they are continuous. They're defined for all real numbers. They are continuous. They may not have any real zeros, but we're not looking for places where it intersects the x-axis. We're just saying from left to right it can be drawn with a single stroke. Okay? May have quite a few ups and downs. But one of the things we looked at besides polynomials in college algebra was rational functions. And rational functions, r of x is equal to p of x or q of x, where p and q are polynomials. Now, q is defined for all real numbers. P is defined for all real numbers. But occasionally, q may be 0. So there are values here that may cause incontinuities. This may or may not be continuous, not depending upon the numerator, but depending upon the denominator. So all the places where the denominator is 0 are points or jumps of discontinuity. So, where q of x equals 0 means discontinuities. Now those discontinuities may be point discontinuities, or they may be infinite discontinuities, but in any event, they're discontinuities. Let's graph another one of these. Okay. Pretty simple one. R of x equals x squared plus 1 divided by x squared minus 1. Okay. What's the domain of that function? Let's talk domain a little bit. When we're finding domains of functions, the supposition going in is the domain is all real numbers. If we're dealing with polynomial, that's certainly true. But if we're dealing with something like a trig function, for instance, the tangent of x, the domain is not all real numbers. It's all real numbers except odd multiples of pi over 2. That pi over 2 is undefined. 3 pi over 2 is undefined. 17 pi over 2 is undefined. Negative 33 pi over 2 is undefined. Infinitely undefined points. But if we look over there once again, well, going into it is all real numbers, and we have, I'll say 3 exceptions. Domain, all real numbers, except I,
What's the first exception? What did we just talk about with our function r of x over there? X squared plus 1 over x squared minus 1. What did we have before we erased this function h of x? For the function g and h, what value of x gave us issues? 1. And when we plugged 1 in, what did it say? It said divide by 0. So our first exception is
Division by 0. That's a no-no.
What's the second exception for ordinary arithmetic? If you consider roots and powers as ordinary arithmetic. What's square root of 9? 3. What's square root of negative 9? 3i. That's not a real number. So, how about the fourth root of 16? Positive 2. How about the fourth root of negative 5? Complex number. Except even roots of negative values. Okay. And then I toss one in. Situation. I have a table which has an area, tabletop has an area of 15 square feet. I know its length is its length is 2 more than its width. What are the dimensions of the table? And clearly the answer is, it's 3 feet by 5 feet. But if you set that problem up algebraically, product of two numbers is equal to 15, and the difference of the numbers is 2. You solve that algebraically and you come up with two solutions. One solution is the width is 3 and the length is 5. The other solution is the width is negative 5 and the length is negative 3. Do negative 5 and negative 3 have a difference of 2? Yes, they do. Is the product positive 15? Yes, it is. But do they make sense if you're a carpenter? I'm sorry, I have to get out my negative ruler. I've never met a carpenter with a negative tape measure. Okay. I've met a few carpenters that owe quite a little bit, but that's a different story. Okay. And that's not all of their doing. You know, they have people that don't pay them. Okay. Last time I paid a carpenter, I paid him $1,200 to build something for me, and after he built it, for the agreed price, he says, you know, I cut my throat on this. It was harder than I thought it was going to be. Sorry about that. Here's your $1,200. Thank you very much. Yeah. Okay. No, I gave it to him. He wanted to retire to get and sell me his business. But, you know, that would be fun to do, but I'd be in the same boat you are. Not making enough to support my family. Okay. So there we are. Situation. So back to this rational expression, rational function, x squared plus 1 over x squared minus 1. And my first question is, what is the domain of that function? All real numbers except, and the only exception is line 2. Or, I'm sorry, exception number 1. It's not line 2. Exception number 1. Exception number 1 is division by 0. What would give us division by 0? 1 or negative 1. And since this does not divide from that, nicely, it's not point discontinuities, it's forever discontinuities. So, at 1 and negative 1, I have excuse me, vertical asymptote.
Well, as x is very, very large, this kind of behaves as x squared over x squared. For instance, if x is 100, 100 squared is 10,000. 10,000 plus 1 is 10,001. 10,000 minus 1 is 9,999. What is 10,001 divided by 900 or 9,999? Pretty darn close to 1. And if we go in the negative direction, at negative 100, we get exactly the same result. 10,001 divided by 9,000, negative or positive 9,999. In each case, is very close to 1. So not only do we have vertical asymptotes, we also have a horizontal asymptote at 1. So, and I notice when it's way out here someplace, oh, slightly greater than 1, slightly greater than 1. And at 0, just for instance, is negative 1. So how do I get from this point up to these points? Excuse me. When this has no zeros. If you solve x squared plus 1 equal to 0, you get x equals plus or minus I. Not real. So this is never 0. So how does it get from here up to there? The answer is, gee whiz, it doesn't. Because you cannot cross a vertical asymptote. You can cross a horizontal asymptote, but you cannot cross a vertical asymptote. So, if we pick some points, well, let's look at limits. We have 4 limits I want to look at. The limit as x increases without bound in the negative direction, r of x, we'll talk about that in a little bit. The limit, actually it's 1, 2, 3, 4, 5, 6 limits. The limit as x approaches negative 1 from the negative side of r of x. The limit as x approaches negative 1 from the positive side of r of x. The limit as x approaches 1 from the negative side of r of x. The limit as x approaches 1 from the positive side of r of x. And finally, the limit as x increases without bound in the positive direction of r of x. All those will help me sketch this graph. We'll go on and find these two in a little bit, but we need to define that. Because we defined limits for a finite situation. You might recall, drawing the pretty little picture, we have some curve up here, we have some value L over here we believe is the limit for some value A down here. And we say that L is limit of f of x at A if given epsilon greater than 0, there exists a delta greater than 0 such that when x minus A's absolute value is less than delta, then f of A minus L will be less than epsilon. Whew. So epsilon and delta are small. Okay, close to 0. Not equal to 0, but close to 0. But in the infinite case, I have to define a little different. We'll do that momentarily. Let's look at these limits. Left and right of here, and left and right of here. So as x approaches negative 1 from the negative side, negative 1.1 squared is positive 1.21. positive 1.21, subtract 1 is positive 0.21. Negative 1.1 squared is 1.21, plus 1 is 2.21. So I have 2.21 at 2.21 divided by 0.21. 2.21 divided by 0.21. Oh, that's about 10. So a tenth to the left of this is about positive 10. And if we go to the other side, 0.9, negative 0.9. Negative 0.9 squared is 0.81. 0.81 subtract 1 is negative 0.19. 0.81 plus 1 is positive 1.81. 1.81 divided by 0.19, say 20 into 180, is again around 9. Not 10, but 9. So it's, and it's negative, so it's down here someplace. And if we look at this one, to the left of positive 1, it's down here someplace. And if we look slightly greater than 1, it's up here someplace. So if we put that stuff together, this comes diving down out there, this comes diving down out there, and this comes up, over, and back down over here. And of course I have x values, make that 0, x, y, okay. Now if you draw it on your calculator, the graph may look like this. Depends on what format your calculator is in. One format says connect the dots. And that's the usual format we have it in. So when you see a graph like this with apparently solid vertical lines, that should be, hey, ding, 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 ding. These aren't solid. It's really a vertical asymptote. If you put your calculator in the mode of just plotting the individual points, when the individual points are along reasonably horizontal, they appear so close that it looks solid. But as you get vertical, they tend to look like they're spaced. You get some apparently gaps, but you won't get that at all. So in the plot the point mode, it'll come up and it'll go down and it'll come down. And here it doesn't show the asymptotes. So of the two, I prefer the connect the dot plot as opposed to don't connect the dot plot. I forget what modes those are, but you know, you play around with your calculator, you can find it. So well, what are these two limits? Clearly, or maybe not clearly, they are 1 and 1. Okay. Wowzers. Okay. Now, if I graph the reciprocal of this function, x squared minus 1 in the numerator, x squared plus 1 denominator, the denominator would never be 0, so the domain would be all real numbers, and you get a smooth curve. But we'd still have x equals positive 1 as a horizontal asymptote. Because back again to college algebra, when we're looking at rational expressions, p of x over q of x, I'm sorry, yeah, p of x over q of x
let's say this is nth degree, and this is mth degree.
If the degree of n, or if n is greater than m, if n is greater than m, then this function climbs without bound. Now whether it climbs to positive infinity or dives toward negative infinity depends upon the signs of the coefficients and the signs of the x's. Same way to the left, it may climb to positive infinity or dive to negative infinity, whether it goes to both up, both down, one up, one down, one up, depends upon the leading coefficients and the powers of x involved. Okay. On the other hand, if m is equal to n, then you have a horizontal asymptote at the ratio of the leading coefficients. In this example, the leading coefficients are 1 and 1, so it has a horizontal asymptote at 1 divided by 1, 1. Not very interesting. On the other hand, if m, the degree of the denominator, is greater than n, the degree of the numerator, it still has a horizontal asymptote, but that horizontal asymptote will be at 0. Goes 0. Okay. Let's look at one.
F of x equals 1 plus sine x over x.
First off, what's the domain of this function? Yeah, all real numbers except 0. Because at 0 we have 1 plus 0 divided by 0. Now, in this particular case, we know the limiting value of sine x over x. That limiting value is 1. We proved that last time in class. But, short run of it, this is not a rational function. Sine of x is irrational. So, we have a couple of issues. What's the missing point at 0? And next up, does it have any asymptotes? Oh, no. That stays 1. That's nice. So what structures this function is this thing. So as x becomes very, very large, the denominator becomes very, very large, or what's the sine of x doing? Draw a sine graph in your mind, or wave it in the air. We kind of start at 0, goes up, goes down, goes up, goes down, goes up, goes down. And that's true in the other direction. Starts at 0, goes down, goes up, goes down, goes up, goes down, goes up. For always. But that is bounded. That number is never larger than positive 1 and never less than negative 1. So if we divide a bounded number, I don't care how big the bounded number is, how small the bounds are, it's still bounded. And if we divide a bounded value by something very, very, very large, what is 1 divided by a billion? for most practical uses, it's 0. So, the limit of f of x as x increases toward positive infinity, or the limit of f of x as x approaches negative infinity, is equal to 1. Because this piece goes to 0. If this were a 1 in the numerator, it would look like that on the right. And if this were 1 in the numerator, it'd look like this on the left. Basically, what we've done is we have bound the function to fit between, and I don't know what it goes like, but fit between there. So it's going to have its wiggles, and its wiggles, its high points, are going to be 2 pi apart, just as they are close to 2 pi apart, not quite, because squishing it causes the high point to shift a little bit. But it's going to wiggle at approximately every 2 pi, but the wiggles will get less and less. Think, how can that be? Well, anybody been out to a pond that has a glass smooth surface in some other state besides Oklahoma, because the wind never doesn't blow here. It's always blowing somewhere, so we don't have a smooth surface. But if it's a smooth surface, and you take a pebble and you drop the pebble into the pond, you get a series of waves. And that impact causes a particular height, but as that energy contained in that wave spreads, that energy that's holding up the high point of the wave per unit length decreases. So as it progresses outward, it gets shallower. From crest to height reduces. Finally, over time, it's dampened back to 0. But you go out far enough, and it would be imperceptible. Same way with tsunami. If you're far enough away, you might notice, oh, that wave came in a little further than the last wave, no big deal. But if you're a little closer to the tsunami, if you're at a coastline, and suddenly the water seems to draw back much further than it did a time ago, you better be heading uphill as fast as you can get uphill, because it's coming back with a vengeance. Because that energy contained in that wave out in the open ocean may be only 3 or 4 feet, but when it reaches the shallows, that energy drives that wave vertically. So what was 3 or 4 feet out in broad ocean, when that energy is displaced due to the shallows, it suddenly grows not a foot or 2, but maybe the 3 or 4 feet becomes 30 or 40 feet, which kind of takes everything away. So, most people think the East Coast is perfectly safe because there's no active volcanoes along the East Coast. Side note, Here's the East Coast, comes down, bulges out a little, then we have Florida. Okay. Out here, off the African coast, the Azores. One of the islands of the Azores is volcanic, and that volcanic cross section will look something like this. And there's a rift right here. And if that rift slides, the East Coast would get a significant tsunami. That won't keep me from visiting the East Coast. What prevents me from visiting the East Coast is I've been there. I don't want to live there. If you've never been to Washington, D.C., great place to visit. I don't want to live there. There are some nice areas there. And the national museums there are just fantastic. You know, Air and Space Museum, Natural History Museum, all of them. Smithsonian Museum, all of them. They're fantastic.
Spy Museum's pretty cool up there too.
Having said that, I have a niece that, if you ever go in the Spy Museum up at NSA, I have a niece that is responsible for the women in spying part of the exhibit. She was a double major at Michigan State, I forget which. Math and English, but her specialty was cryptology. To this day, we don't know what she did, but after about 20 years of it, she says, my brain was fried and I had to get out of it. And she became assistant curator to the museum. And so she did the women in spies, the Mata Hari and other spies.
It's like 20 years since I've been there. But
Yeah. 20 years ago. Yeah, I think she had just moved over there about then. So maybe something of hers was there, maybe not.
I could also just be pulling that number out of nowhere though too.
Yeah.
I vaguely remember that.
Yeah, well, you were young.
Oh yeah.
20 years ago, I wasn't very young. I was young. Okay, so let's formally define limits at infinity. Okay. Limit as x approaches infinity of f of x is equal to L if given epsilon greater than 0. Looks just the same so far. Excuse me. There exists elm greater than 0. When you have great means very much larger than 0. There exists m greater than 0 such that for all x greater than m, f of x minus L in absolute value is less than epsilon. And there's another one in the negative direction. Limit as x approaches negative infinity, f of x equals L. Again, the same words, but the only difference will be m much less than 0. There exists all x less than m. Excuse me. It's weather, that is. 15 below one day and 70 above the next day. And my lungs are not what they used to be when I
kid, my density was greater than 1, so I could sit on the bottom of the pool and not bob to the surface. I could sit on the bottom of the pool for over 2 minutes. Used to go swimming at a public pool and sit on the bottom of the pool for 2 minutes, see if the lifeguard would come in. Only if the good-looking girls were the lifeguards. They never did. They would have let you drown. I thought, man. But now I can hold my breath for about 27 seconds and then pass out. Okay. So we know limits at infinity, anyway, by definition. Now we have the concept of continuity. We have a quiz on Wednesday. And also that's when the activity is due. And what I want to do for the next amount of time is work some problems in sections 2.5 and 2.6. See if we can get some reasonable results. So, because of the number of problems there, I think I'll start with number 2 in each section. But instead of doing every other even, I'll do skip 8. So 2, 10, 18, and so on. Let's work a few of those and see what it says. Okay.
So, I think page 100 is where we began. Maybe. That seemed to come to mind. Yeah. Exercise is 2.5. And number 2 is a function that looks something like this. It starts at -1, a little above 0. It crosses the axis at 1. And it climbs up to some point up here. I think that point is, it's just 2. Climb too high. Climbs about there. And then it dives again back to there. Okay. So the function looks like that. And it asks us in exercise 1 through 4, say whether the function graph is continuous on the closed interval from 1 to 3. -1 to +3. On the closed interval from -1 to +3. So on the closed interval from -1 to +3, is this continuous? And the problem is here. We're missing that value at 3. Okay. We're talking about continuity, and a point is included. If this is where the domain quits, we say it is continuous at this point because the limit from the right exists and is equal to the function value. Over here, this limit exists, but there's no function value. So this is not a continuous function. Okay. There's nothing wrong with a cusp. Okay. Perfectly good function to have a cusp in it. Most common function you see that has a cusp is an absolute value function. Comes down to a single point, goes up in 2 directions. This comes up to a single point, goes down in 2 directions. That's perfectly okay. That's not an issue. Now, in the not too distant future, when we talk about a smooth curve, then that is an issue. This curve is not smooth. If you're driving a race car along this track, right turn, right turn, right turn, left turn, left turn, instantaneous turn. Left turn, left turn, left turn. What's the acceleration necessary to do an instantaneous turn? Infinite acceleration. Much lower than that value would already be jelly. So you can't survive that. So it's not a smooth curve. Okay. We like smooth curves. Okay. And we'll have to define that sometime in the future. Number 10. Okay, again, they draw me a picture. And the picture, again, goes from -1 to +3. And it starts at -1 and swings down as looks like a quarter arc to an open point. Has no point at 0, climbs to 1, 2, where there's an open point, dives to 2, 0, there's an open point, and continues on to 3, and there's an open point. So, and the question asked for these, number 10, to what new value should f of 1 be changed to remove the discontinuity? So what value do we want to assign to f when x equals 1 to get rid of that discontinuity? 2. And we can get rid of that discontinuity at x equals 2. Then f of x, if we assign 0, it works. Same thing here, if we assign 0, it works. But here, we cannot get rid of this pair of discontinuities. Because no matter what value of f of x you choose, it misses one point or the other. So that is not a removable discontinuity. These are removable by the appropriate selection of points. Number 18. Where are we on number 18? Ooh, kind of interesting. Y equals 1 over absolute x plus 1 minus x squared over 2. Y equals 1 over absolute x plus 1 minus x squared over 2. Did I copy that right? I think this morning when I worked that, I left off the x squared over 2. That's okay. And for these, it says, at which points do the functions in exercise 11 through, at what points are the functions in exercises 13 through 32 continuous? Okay. Now, what are our requirements for our domain? All real numbers except division by 0, and even roots of negative numbers. Is 2 ever equal to 0? No restriction there. Is absolute value ever equal to 0? Absolute value is equal to 0, but 0 plus 1, this denominator is always positive. This denominator is always positive. There's no restriction on x. So this is a continuous function with a cusp. Kind of interesting. A continuous function. (18 plus 8 is 26. 26y equals the fourth root of 3x minus 1. Y equals the fourth root of 3x minus 1. What's the issue on this one? There's no denominator, so nothing to worry about there.
even roots of negative values. So what restriction do we have to put on that so that we don't have that issue?
Well, let's see. X minus 1
Must be greater than or equal to 0. That's not too hard to solve. Add 1, divide by 3.
x must be greater than or equal to 1/3.
So from 1/3 on, this is continuous. To the left of 1/3, it's not even defined. So my domain greater than or equal to 1/3. Okay. 34. Limit as t approaches 0 of the sine of pi over 2 cosine times tan
Y is equal to the sine of pi over 2 cosine t.
What issues do we have with this thing? Number 34 says, find the limits, and we want the limit as t approaches 0.
Limit as t approaches 0.
Well, let's look at, oh, I missed one. Cosine of the tangent of.
Cosine of the tangent of t. Close tangent, close cosine, close sine.
Ooh, okay.
Close limit.
Helps to have all the pairs of braces, brackets, parentheses, braces, brackets. Oh, yeah. Parentheses, brackets, braces. Well, let's see. Is tangent well defined at 0? Yeah, it's effectively 0. Is cosine defined at 0? Yeah, cosine is 1. Is 1 times pi over 2 defined at 0? Yeah, it's pi over 2. Is sine of pi over 2 defined at 0? I mean, at pi over 2. Sine of pi over 2 is 1. Oh, so this limit is 1. But the function as a whole has issues. Not because of the sine function. It's good for all real numbers. Not because of the cosine function. It's good for all real numbers. But the tangent function is an issue. Because the tangent function is undefined, again, every odd multiple of pi over 2. If that were a cotangent function instead, or a secant function instead, or a cosecant function instead, it may have different issues. If that's a cotangent function, then the issue points are at even multiples of pi over 2, or just multiples of pi. 0 pi, 2 pi, 3 pi, negative 37 pi. Because the tangent of 37 pi over 2, undefined. Come out from one side, takes off to positive infinity. Come out from the other side, takes off to negative infinity. Number 42. I'm sorry. Yeah, number 42. Okay. define h at 2 in a way that extends h of t equals t squared plus 3t minus 10 divided by t minus 2 to be continuous at t equals 2. X squared plus 3t minus 10.
Because it's plus or minus 3x.
Plus
X minus 2? At x equals 2, we have division by 0. But nicely, the numerator factors. So everywhere the x is not equal to 2, this behaves like x plus 5. Well, what is the value of the function x plus 5 at x equals 2? 2 plus 5 is 7. So if I define my function y equals x squared plus 3x minus 10 over x minus 2, comma, when x does not equal 2, and equals 7 when x does equal 2, we filled in the hole. Number 50. Okay, piecewise, g of x equals 3 pieces. Piece 1, ax plus 2b. ax plus 2b for x less than or equals 0. And x squared plus 3a minus b, x squared plus 3a minus b, where 0 is less than x is less than or equal to 2. And 3x minus 5 for x greater than 2. Okay. This last part's a line. This part, second degree, is a parabola. First part, with real numbers a and b, that's also a line. So somewhere in here, depending on the values of a and b, we have a line, we have a parabola, we have a line, and we want to fix it so that these connect at 0 and 2. Okay. The only one that we have a definite value is this one. At x equals 2, 3 times 2 is 6, minus 5 is 1. So at x equals 2, we want g of x equal 1. So we take this value and insist that that is 1 when x is 2. So 1 is equal to 2 squared plus 3b minus, plus 3a minus b. Do the arithmetic, simplify it. 3a minus b equals negative 3. I know what a and b are. But when x is equal to 0, I want this one to be the same as that one.
Well, when x is equal to 0, what does that say? 2b. Has the same value as, yeah, let's put this back to, let's leave it, move the 1 over there, okay. Let's write it this way, 3 plus 3a minus b. That's the function value. No, I'm sorry, I missed that. What is this at 0? Because we're looking at 0 and 0. What is this at 0? That goes away, we just have 3a minus b. So I have 2b is equal to 3a minus b. Add b to both sides. 3b equals 3a. That makes things nicer. That says a is equal to b. So we go back to this. Wherever. If a is equal to b, this becomes negative 3 is equal to 3a minus a. Negative 3 is equal to 2a. A is equal to negative 3 halves, which means b is equal to negative 3 halves. Now let's test this. Negative 3 halves x minus 3 is that one. This one becomes x squared plus 2 x squared minus 3. This remains 3x minus 5. At 0, this is negative 3. At 0, this is negative 3. These are now continuous. At 2, this is 1. At 2, this is 1. So now it's continuous. This feeds into this, which feeds into that. Takes a little algebraic manipulation, but you're testing the points 0 and 2, because that's where they break the domain. They have a domain for this part, domain for this part, domain for this part. You check where the domains overlap, or almost overlap. Okay, let's look at section 2.6. Look at some limits. Again, that same series of problems. Number 2. See if I'm drawing this thing. Been attacked. Come on. I know you stay up there. Negative 6 to 6. 6, 5, 4, 3, 2, 1, 0, 1, 3, 4, 5, 6. 5, 4, 3, 2, 1, 0. Okay. This graph looks like it begins at somewhere to the left of negative 6, dives down, goes up through about 3.5, negative 3.5. So it starts, where's that? Yeah. It starts somewhere down here, dips a little,
comes up through about 3.5, negative 3.5, then heads up to 3. This way, it dives down from here toward, goes through negative 2, goes through negative 2, and dives this way. Where does it dive to? Oh, it goes all the way over to 0. Dives whoop, toward 0. Okay. Then starts up high and goes to about 1, 2. Starts up high, goes to about 1, 2. Is that open or closed? I'm sorry, goes to 2, 1. That's closed. Okay. Then from there it starts way down, comes up through close to 3. Starts way down, comes up close to 3. Does a little loop and dives toward this and goes that way. Okay. Negative 6, negative 3, negative 2, positive 2, and so on. Okay. So, and here it does not show an arrow, it just stops. Here really goes on, so we have the vertical asymptote there. We have vertical asymptote here. We have vertical asymptote here. Okay. So what does it ask about number 2? For the function f whose graph is given, determine the following. So basically it's a limit at all the different points. The limit at, and this is actually shows right there. The limit at negative 6 appears to be negative 1. Okay. As we approach negative 3, the limit increases without bound. On both sides, both go to positive infinity, but doesn't mean they're connected. They are not connected. They both go to positive infinity, but they're not connected. And then as it approaches 0 from the negative side, it goes to negative infinity. As it approaches 0 from the positive side, it goes to positive infinity. As it approaches 2 from the negative side, it goes to the value 1. As it approaches 2 from the negative side, it approaches the value negative infinity. And then the limit toward positive infinity appears to be, well, they don't draw an arrowhead on that either. Since the arrowheads are not drawn, we can assume it stops there. But if the indication, if they put an arrow on it, as I think they should have, then this we'd say limit as it approaches negative infinity appears to be negative 1. This limit as it approaches positive infinity appears to be 0. Okay. Number 10. Find the limits. Limit as theta approaches negative infinity of cosine theta over 3 theta. Cosine theta on 3 theta, the limit as theta approaches is a negative infinity. Well, again, what are the bounds on cosine? What are your upper and lower bounds on cosine?
1 and negative 1.
1 and negative 1. It's bounded. As theta approaches negative infinity, what does 3 times theta do? Approaches negative infinity even faster. What is a very large number divided into something between negative 1 and positive 1?
it approaches 0. Now, having said that, at 0, this is 1 over 0, way up there. Okay. But it's in the negative direction, so way down there. So this wiggles that way. On the positive side, it wiggles that way. Limit at negative infinity is 0. Okay? It oscillates slightly above, slightly below, slightly above, but that separation is getting smaller and smaller. So given epsilon greater than 0, there is an m such that anything beyond that m gives you a value less than that from the limit. Okay, number 18. In 13 through 22, find the limit of each rational function, a, as it approaches positive and negative infinities. Number 18. 9x to the fourth plus x, and then a denominator. Go back over here. H of x, 9x to the fourth plus x divided by 2x to the fourth plus 5x, 2x to the fourth plus 5x squared minus x plus 6. So this gets us back to college algebra. What's the degree of the numerator? What's the degree of the denominator? So what's the limit as this goes to positive infinity? If the degrees are the same, the limit is the ratio of leading coefficients. 9 halves. The limit as x increases without bound of h of x is 9 halves. Limit as x increases without bound in the negative direction, h of x is 9 halves. Because when x is large, these other terms are nothing. If x is 1,000, 1,000 to the fourth is a trillion. A trillion plus 1,000 is close to a trillion, times 9 is close to 9 trillion. 2 trillion plus 5 million. If you check it, the national debt, it's about 20 trillion now. 5 million is nothing. So we have approximately 9 trillion over 2 trillion, which is pretty close to 9 halves. Okay, that was number 18. Number 26. The limit as x increases without bound of x squared minus 5x over x cubed plus x minus 2. And the square root of all that. So we have square root. Is that what it said? Number 26. X squared minus 5x. X cubed plus x minus 2. We want to know the limit of this thing as x increases without bound. Well, let's disregard the square root for a moment. Well, maybe not. We need to speak to it. Since this is a cubic polynomial in the divisor, this has one place at least where this is 0, and that is at x equals 1. 1 plus 1 minus 2 is 0. So this is, we have a vertical asymptote at x equals 1. And there may be two others. If you go on and solve this completely, it may give you two more real numbers, or it may give you a complex conjugate pair. Okay, I don't know, but at least one point in close where we have issues. But that's not what it's asking. It's asking, what do we got way out there? So what do we got way out there? Way out there, in the positive sense, is positive infinity. In the positive sense, it's positive infinity. If we're looking on the negative side, we would run into issues real quickly, because the negative value cubed would dominate, and we cannot take the square root of a negative value. So, they didn't ask us to look that way, fortunately. They just asked us to look that way. So if we're looking to the right, to the positive side, we have second degree divided by third degree. Let's not worry about the square root sign, because on the positive side, far enough positive, they're all positive. That positive divided by positive, so the square root would be positive. But square root of what? Under the radical is a rational expression. With the rational expression, the degree of the numerator is 2. The degree of the denominator is 3. 3 overpowers 2. Denominator gets big faster than numerator. This goes to 0 inside. Square root of 0 is 34. Same game. Limit as x approaches negative infinity of x squared plus 1 square root over x plus 1. Does it say x plus 1? Limit as x approaches negative infinity. What's numerator approach? What's any large number squared is a large number. Plus 1 is still a large positive number. The square root of a large positive number is still a large positive number. And as x increases without bound in the negative direction, this is a large negative number. Coefficient-wise, how do the coefficients behave? This behaves very close like x over x. Not exactly, but pretty close. Because this is negative, this is positive, leading coefficient in each case is 1. Number 42. Limit as x approaches negative 5 of 3x over 2x plus 10. Well, I'm sorry, as approaches negative 5, does it have a direction on that? Negative 5 from the negative side? Okay. 3x over 2x plus 10. 3x over 2x plus 10. The limit
as x approaches -5 from the negative side. So from the negative side, maybe like -5.1, what's twice -5.1? -10.2. -10.2 drag 10 is -0.2. In the numerator, 3 times -5.1 is -15.3. -15.3 divided by -0.2 is about 60. I'm sorry, 15. What's twice 15? About 30. About, no, 10 times. 5 times 15. About 75. I'll get that out. This is negative, that's negative. The ratio at -5.1 is about 75. So this appears that this is going toward positive infinity. And let's look at 50 and call it a day. I'm looking at 50, I'm calling it a day.